Alright, hi. Alright, covering non-resident training course, September 1998, Navy Electricity Electronic Training Series, Module 13, Introduction, Number, Systems and Logic, NAVED, TRA 14185, Distribution and Statement A, approved for public release, Distribution Unlimited. Chapter 1, Number Systems. Chapter 2, Fundamental Logic Circuits. Chapter 3, Special Logic Circuits. Appendix 1, Glossary. Appendix 2, Logic Symbols. Index. Alright, throughout the section of the course, well, you have the technical manuals associated with the equipment you will be working on. You will find below the notation and some of the paragraph notation for the emphasize the safety hazards. This care must be taken and observed. Warning, operating a procedure, practice, or condition, etc., which may result with the injury or death if it's not carefully observed or followed. Caution, an operation, procedure, practice, condition, etc., which may be result with the damage if the equipment not carefully observed or followed. Note, an operating procedure, practice, condition, which essentially emphasizes, Chapter 1, Number Systems. Learning objective. The learning objective is with the beginning of each of the chapter. The learning objective is with the preview information with the objective of the learning chapter. The comprehensive checks to questions are based with the objective of the basic successfully with the NRTC. You indicate that you must have the objective of the learned information learned objective listed below. Upon the completion of the chapter, you should be able to do the following: recognize the different type of the number shifts to relay with the computers, identify the define unit number, base radius, positional notation, most and least significant digits as they result of the decimal, binary, octal, hexadecimal number system. 3. Add, subtract binary, octal, hexadecimal system number system. Convert value of the decimal and binary, octal, hexadecimal, binary code decimal number systems to each other and back to the other systems. Add in binary code decimal. Introduction. How many days leave do you have on the books? How much money do you have the less in the payday? It doesn't matter what the question is. Any of the dollars or dollar days or cows, it will be represented by numbers. You just try to imagine going through the one day without using the numbers. Some things can easily be described without using numbers, but others prove to be difficult. Look at the following example. I'm stationed in an aircraft in Neets. How he owns a green Chevrolet. Use the number that's necessary for the preceding statement. The following example depend on the use of the number that I have $25 last until payday. I want to take 14 days to leave. You can see that these statements of the numbers play an important role in our lives. Background and history. Man's earliest number of the counting system was probably developed with the help of determine how many of the possessions a person had. Daily activities became more complex. The numbers became more important. Time, trade, distance, and all other phases of the human life. As you have seen over, the numbers are extremely important with the military, personal life. You realize that you use them more than your fingers and toes to keep track of the numbers in daily routine. Even since the discovery of the necessary for the count of the objects, looking for the easier way to count them. The abacus, developed by the Chinese, is one of the earliest known calculators. It's still used in some parts of the world. Pascal, French, invented the first adding machine in 1642. 20 years later, the Englishman Sir Samuel Morland developed a more compact device that could be multiplied, add, or subtract. By 1672, the Gottfried Wilhelm Eisen Libyans German perfected a machine that could perform all the basic operations: add, subtract, multiply, divide, as well as the extract, square root. Modern electronic digit computers will still use the von Neumann principles. Modern use. Common computers are now employed wherever the repeated calculations are processing a huge amount of the data. Even the great applications are found with the military, scientific, commercial field, but they have the application for the brains of the mailing, sorting through engineering, design, identification, and construction of enemy targets of any of the digital computers, including speed, accuracy of the manpower, so everything other computers are able to take over the routine job of the release personnel for the more important work that can be handled by a computer. Alright, computers do not normally speak with the same language. The method of the translation in the form of the understandable, usable, the both necessary. Humans generally speak in the words and the numbers expressed with the decimal numbers, while the computers on the other only understand codec electronic pulse to represent the digital information. In this chapter, you will learn all about the numbers of the general and about binary, octal, hexadecimal, which refers to hex number system, specifically members of the converting of the number, the binary, octal, hex system, equivalently number to the decimal system, and vice versa, which will also describe. You will see the number systems can easily be converted to the electrical signal necessary for the digital equipment. Type of number system. Unit. Now that you have probably only one number system for the decimal system, you may also be familiar with the Roman numeral system, even though you seldom use it. The decimal number system, the module, will be studying the modern number system. You should realize that these systems can have certain things in common. The common numbers will be defined with the decimal system as our base. Each term will be related to each of the number of the system when the number of the system is introduced. Each number of the system you will study the built around with the component for the unit, number, and base radix. The unit number, the term the unit and number will be with the decimal system, almost self-explanatory, but the definite unit itself of the signal object is an apple, $1 a day. A number symbol representing with the unit of the quantity figures 0, 1, 2, 3, and 9 are symbols with the decimal system. These symbols are called the Arabic numbers, and figures other symbols may be with a different number system. For example, the symbols U for the Roman numeral systems are letter V with the symbol for the F5, or X for the letter 10, M for the 1000. You will use the Arabic number letters for the number systems in discussion in chapter. All right, your base radix. The base or radix number of the cells you for the number of the number of the symbols you within the system. The base of the item, basically any of the system is also always expressed in decimal number. The base and radix of the decimal system is numbered to 10. This means the 10 symbol is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 used in the system. And the number of the system using the 3 symbol 0, 1, and 2 would be the base, and 3 would 3, 4, 3 would be the base would be 3. 4 symbols would be a base of 4, and so forth. Remember to count the 0 with a symbol, the U with a 0 with a determining the number of the symbol for the U within the number system. The base of the number system is indicated with a subscript, the decimal number of the following, the value of the number of the following example, the numeric value with a different base with a subscript to indicate the base. For instance, 7,592 with 10 numbers, 214 with 5, 123 with 4, 656 with 7. You should give the highest value symbol the U for the number system, then always use one left for the base for the system, and the base is 10, largest value with the symbol is positive. In the base 10, the largest value symbol is 9, and the base of 5 is 4, and the base of 3 is 2. Positional notation is 0. With the reserve of the two principles accounting with the writing of the quantity with the numerical value, with also the positional notation and 0 principle. Positional notation system, the value with the number is defined with only by the symbol, but by the symbol, not only by the symbol, but by the symbol's position. Let's examine the decimal base number 10 value, the 402 value of 427.5. You now, from the experience, the value has 427 and a half. Now examine the position of each number. All right, the 4 represents 400 units, or 2 represents 200 units, 7 represents 7 units, 0.5 represents a half a unit. At 427.5 quantity you wish to express for each of the number of the position is shown. If you exchange the position 2 and 7, you change the value. Each positional notation represents the number represents a power base or radix. A power is the number of the times the base is multiplied by itself. The power is written above the top right of the base. If it is called the exponent, examine the following base for the 10-line graph: 10 to the third, 10 to the second, 10 to the first, 10 to the 0th, 10 to the negative, 10 to the radix points. Also we have 10 to the third, which is equal to 1,000. 10 to the second was 100. 10 to the first, 110. 10 to 0, any number raised to the power of 0 equals 1. 10 to the negative 1 is a tenth. 10 to the negative second is 100th. 10 to the negative third is 1,000. Now let's look at the value with the base number 10, 427.5 of the positional notation line graph. 10 to the second is 4, 10 to the second, 4 is 10 to the second, 2 is 10 to the first, 7 is 10 to the 0th, 0.5 is 10 to 1.5, so you'd have 400, 207, and 5. You can see the power base is multiplied by the number of the position to determine the value for that position. The following graph illustrates the progression of the powers of the 10. 10 to the 4th, 10 to the 3rd, 10 to the 2nd, 10 to the 1st, 10 to the 0th, radix point, 10 to the 1st, negative 1st, 10 to the negative 2nd, 10 to the negative 3rd. All number to the left of the decimal, while the whole number to all the number to the right of the decimal point, fractional number, the whole number simply represents one or more, complete with the object with the subject, with the one apple to $5. A fractional number system, the symbol represents the portion of the object with the half an ample with a quarter of the dollar. The mixed number the represents the one with the more complex object with the sum of the portion of the object, such as one or half of the apples, 1.5 amples. When you use any of the base other than the decimal division between the whole number and the fractional number, this is referred to the radial exponent of the decimal, but the actual radial exponent of the decimal of the system of the term radial exponent is normally not used with the base of the 10 number system. Just important with the positional notation is use the zero, the placement of the zero number that can have quite an effect with the value when being represented with the same position for the number that does not have the value between 1 and 9. Consider how would it be effect with the next paycheck. If you were expecting the check of the $604.47, you would want to be 600. You wouldn't want it to be $65.47, leaving out the zero that can cover the mean of the difference of $540. If the number is 605.47, then zero indicates that there's no tens. If you place that value on the graph, you will see that there no multiplier for the number 10, negative 10 to the 1. 10 to the second and 10 to the first is 0, 10 to the 0 that is 5, the radial exponent 10 to the negative 4 for the 10 to the negative second, the 4 and 7. Most significant digit, most significant digit, and least significant digit, MSD and the LSD. Other important factor for the numbers you should recognize the most significant digit and least significant digit. The most significant digit is in a number if the digit that has the greatest effect on that number. The least significant digit is the digit that has the least effect on the number. Look at the following examples. All right, your most significant digit would be 1 and 1,876.0 would be 1. 473.022 would be 4. And 0.03269 would be 3. Your least significant digit would be 6 for 1,876, and 473.022 would be 2. And 0.03269 would be 9. You can easily change with the most significant digit will increase the degree of the value with the number of the greatest amount. The change with the least significant digit will have the same effect of the value with the non-zero digit with the number that is far to the left of the zero with the most significant digit with the non-zero digit farthest to the right, and the least significant digit as in following. The most significant digit and less significant digit. And the whole number of the least significant digit will always be the digit immediately to the left of the radius point. In whole numbers, okay? All right, your carry and borrow principle. Soon after they learned how to count, you were taught how to add and subtract. The time to learn with some of the principle you also want to add with the concept of the review within you with the decimal shift. They always apply with the other number shift them you will study. Addition is in the form of the counting with which one quantity is added to another. The following definitions identify with the base of the term addition. Adgend is the quantity with which is added added. Added is the number to be added preceding the number. Sum. The result of the addition, sum of the 5 is 7, and 5 and 7 is 12. The carry is probability for the sum of the two more digits of the vertical column equal to the exceed of the base number of the system. How do we handle with the carry? The two digits of the number generally with the carry the producer of the low order become the sum of the column and the being added. The higher order the digit of the carry that is added with the next higher order column. For example, the left added 15 and 7 in the decimal. The carry would be 1 from 15 and 7 would be a carry of 1, making it 22 sum. Starting in the first column, we find that it's the sum of the 5 and 7 of the 12 of the 2 become the sum of the large for the order column of the 1, and then carry the add for the upper order column. The sum of the upper order column of the 2, but the sum of the 15 and 7 is therefore 22. The rules of addition are basically similar regardless of the number of the shift of the being u. Each of the number shift them become the different number of the digit that will have the unique digit and addition table. The additional table described during discussions of the adding the process of each of the number of the system. Decimal addition of the table is shown with the table of 1 1. The number of the rows x in column y represents either added or ogagen. The number of the x represents the ogagen, and the number of the y must represent the added in, vice versa. So the x and y are located at the point of the array z where they select the x row and y column intersect. Table 1-1 shows the decimal addition table. The two add 5 and 7 the u of the table. The first located the number of the one x row, and then the other y column. The point of the z with the row of the column intersect with the sum and indicate for the sum of the 12. Subtraction. The following definitions identify the basic terms you will need to know understand with the subtraction operation. Subtract to take it away with the power of the whole number, the one number from the other. The miniden is the number which the number is to be subtracted. Subtrahend is the quantity to be subtracted. Remainder and difference of that was left after the subtraction. Borrow and transfer. digit equal to the base number of the next higher order in column for the purpose of subtraction. Even the rules of subtraction for subtract 8 from 25. The form of this problem is probably familiar to you. So you'd have 25 at the minute end, 8 is subtraction, 17 is the difference, and a carry of 1 and 15. You require the u for the bar with a can subtract 8 and 5 with the positive difference. You must u for the bar with 1. Really, one group of 10, one group of the 10 plus 5 groups of the 1 equal to 15. 15 minus leave the difference of the 7. This would reduce the 2 by the bar with nothing, and this would be subtracted brought down to the difference. Since the process of the subtraction and opposite addition for the addition table of 1, 1 may be with the illustration subtraction facts for any number system we may discuss. I would say in the addition x plus y is equal to z. Subtraction reverse is true that the y times y minus z minus y is equal to x, or z minus x is equal to y. Thus, the subtraction minute in is always founded by the array of g, but the subtrahend is either row x and column y. With the subtrahend of the row x, the remainder will be column y. With the conversely, with the subtrahend of the column y, with the difference of the row x. For example, the subtract 8 from 15, find that either x or y column. Find whether the two rows column intersect with the value of the 15 for z. Then move the remaining row of the column. Find the difference. Your binary number system. The simplest possible number system is the binary system, or a base of 2 system. You'll be able to use the information we just converted with the decimal system easily to relate the same term with the binary system. Unit number. The base and radix you should remember from our decimal section. The number of the system u with the number of the system. Since the base is 2, the only two symbols would be 0 and 1 are u. The base of the indicator of the subscript are shown in the following example. 1 with a base of 2. When you're working with the decimal system, you normally do not use the subscript, but you will be working with the number system other than the decimal system. It's important to use the subscript so that you are sure of the system being referred to with the following two numbers, 11 and 11. No subscript that you should would be assumed both values were the same. If you add a subscript to indicate the basement system you shown below, that their values are quite different. 10 to the 11 to 10 base. And 11 with a 2 base. The base 11, 10. The base 10 number 11 is 11. The base 2 number 11 2 is only equal to 3 in the base of 10, is only equal to 3 in the base of 10. There will be occasions where you will be more than one number that we'll discuss at the same time, so you must be proper to subscript. Positional notation. As a decimal number system, the principle of the positional notation applied with the binary number system, you should be able to recall the decimal system u for the powers of 10 to determine the value of the position. Binary system u for the power of 2 to determine the value of the position. Bar graph showing the position of the power of the base that's shown below. Alright, 2 to the 4th, and 2 to the 3rd, 2 to the 2nd, 2 to the 1st, 2 to the 2nd, 0, 2 to the negative 1st, 2 to the negative 2nd, 2 to the negative 3rd. 2 to the 4th equals 16 to the 10th. Okay? 2 to the 3rd equals 8 to the 10th. 2 to the 2nd equals 4 to the 10th. 2 to the 1st equals 2 times 1 or 2 times 10. 2 to the 0th equals 1 to 10. 2 to the negative 1st equals 1 half or 0.5 to the 10th with a subscript of 10, the base 10. 2 to the negative 2nd equals a quarter, 0.25 to the base of 10. 2 to the 3rd equals 1/8 or 125 to the base with a 10th. All numbers of the value of the left of the radix point with a whole number to all numbers of the right of the radix point are fractional numbers. Let's look at the binary number 101.1 on the bar graph. 2 to the 2nd would be 1. 2 to the 1st would be 0. 2 to the 0th 2 to 0 would be 1, and 2 to the 2nd would be negative 2. Work on the radix point from the right to left of the determine the decimal number. The equivalent 1 times 2 to the negative 1st would be 0.5 to the base of 10. 1 to the 2 to the 0 to 1.0 to the base of 10. 1 times 2 to the 1st would be 0.0 to the 10th. And 1 times 2 to the times 2 would be 4 to the 0, 4.010 to the base of 10 would all equal a base of 5.5 to the 10th. Table 1 provided the comparison with the decimal binary number to notice for each time of the total number of the binary symbol, the position, increase of the binary number to indicate the next higher power to the second. By example, you can also see the more simple position the need of the binary system represented by the equivalent value of the decimal system. Alright, so 10 to the 1st would be 0, 10 to the 2nd is 0, 10 to the 1st would be 2 to the 1st, 100 binary would be 2 to the 2nd, or a decimal 4, 8 would be one binary decimal. 8 would be 1,002 to the third. 10 to the first would be 10,000. 10 to the second. 10 to the second. 10 times decimal 10. All right, 2 to the fourth in binary would be 10,000. Your most significant digit, least significant addition. When you determine the most significant digit and least significant digit for a binary number, you use the same guidelines you use with the decimal system as you read left of the right, the first number in the non-zero digit you can encounter the most significant digit. Last non-zero digit is the least significant digit. If you number the whole number to the first digit and left of the radix point with the least significant digit, you'd have the most significant digit 1, least significant digit 1, and then the radix point. Most significant, least significant digit, radix point. Here is the decimal system. The most significant digit will have the most effective of the number. The least significant digit will have the less effective of the number. The two numbers of the binary system are 1 and 0 that can easily represent with any electronic device. For example, the 1 is the second that may be the indicator of the device active and also 0 to the base of 2 may be indicated with the device not active on off. So 0 would be off, on would be 1, off would be 0, on would be 1. Looking at the preceding figure of the illustrator of the very simple of the binary counting device, note that 1 to the second is indicated with the lighted lamp, and 0 to the second is indicated with the unlighted lamp. The reverse will work equally well with the unlighted scale. The state of the lamp that can be used to represent with the binary 1 condition, lighted state with the represent with the binary 0 condition. The both method used with the digital computer application. Many other devices are used to represent with the binary condition. They include switches, relay, diodes, transistors, integrated circuits, or ICs. Additional binary numbers. Additional binary numbers basically the same in addition to the decimal numbers. Each system have the augmented, addendum, sum, and carries the following examples to refresh your memory. 15 is augmented, 7 is added in. You get a sum of 22. The carry was 1. Simply only two symbols of 0 and 1 are used with the binary system with the four combinations or additions. 0 plus 0 is 1. 1 plus 0 is 0 plus 1, and 1 plus 1. For some of the first three columns, 0 plus 0 is equal to 0 to the base of 2. 0 plus 1 is equal to 1 to the base of 2. 1 plus 0 is equal to 1 to the base of 2. For the combination represent the different situation, the sum of the 1 and 1 in any other number of the system is 2, but the number 2 does not exist in the binary system. Therefore, the sum of the 1 and 2, 1 to the base 2 and 1 base 2 is equal to 10 base 2. Spoken as 1, 0 base 2 is which is equal to 2 to the base of 10. So you'd have an augmented 1 to the base of 2 plus 1 added into the 1 plus the base of 2. You get a carry of 1. You get 10 to the second, 10 to the base, 10 to the base of 2 sum. So in the following example, the four combinations mentioned above, the 101 augmented to the base of 2 plus 10 to the added in the base of 2 equals 111 added base of 2 sum. All right, your carry 101 augmented in with plus 101 added in equals 10 to 10 to sum carried. When you carry the produce, when carried, produce notated with the column next higher value with the column immediately left of the one with the produce for the carry. The example of 100 and 110 1011 is the base of 2 and 11 012. Right to solve it. Right as a solution. Write out the problem solved. The 101 101 to the base of 2 augmented plus 11012 to augmented with the base 1101 augmented base 2 added in. As we noted previously, the sum of the 1 and 1 is 2, which cannot be expressed in a single digit in the binary system. Therefore, the sum of the 1 and 1 produces a carry. All right. You get the carry. It would be 1 and 1. You get a carry 1 augmented in and added in. The following steps which carry they indicate the show of the completion. When the carry is added, you have you'd have 11. You carry the 1 over. You'd have 11 0002. The final step remaining with the carry that brought down with the sum of the following example will be seen the more one carry may be produced with a single column of the sum that does not occur with the decimal system. Add 1 to the base 1 base 2, 1 base 2, 1 base 2, and 1 base 2, 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 1 base 2. Added together, the sum of the added and the first of the 0 with the will carry with the sum of the second and third added is 0 with the will carry. At this point, the reasonable resembles a carry is 0 to the number 2. The sum of the 0 will with a carry. The sum of the problem is false. You get 100 with the base of 2. The same situation curve with the following: the 100 base of 2, 101 base of 2, 111 the base of 2. 100 to the base of 2 is all getting in, 101 added in, 111 added in. You get you carry the 1, you carry another 1, and then you'd have it so far, and then you'd have 10,000 to the base of 2 sum. Additional binary numbers should be remembered the following binary additional rules. Rules: 0 base of 2, 0 plus 0 base of 2 equals 0 base of 2, 1 base of 2 plus 0 base of 2 equals 1 base of 2, 0 base of 2, 0 base of 2 plus 1 base of 2 equals 1 base of 2, 1 base of 2 plus 1 base of 2 equals 10 base of 2. Now practice what you've learned with the solve the following problems. And then subtract with the binary number. Now if I were familiar with the additional binary number, the subtraction will be either the following of the 4 rules you may observe the subtraction. The 0 to base of 2 minus 0 base of 2 is 0 to base of 2. 1 base of 2 minus 0 base of 2 is 1 base of 2. 0 base of 2 minus 1 base of 2 is 1 base of 2. 1 base of 2 plus 1 base of 2, 1 base of 2 minus 1 base of 2 is 1 base of 2 with a borrow. For example, 1011 base of 2 minus 1100 base of 2 to demonstrate the 4 rules of binary subtraction. Minute in 10,110 base or 101102. Subtracted in 1100 subtrahend would give you the difference of the and then rule 4 will be explained. Rule 4 represents the differential situation because of the cannot subtract 1 from 0, of the cannot subtract 1 from 0. You have a pi with the difference. You must borrow the 1 in the next higher order column of the minute in. The borrow may be indicated as shown below. All right. The rule would be you'd have a 10 to 10, 0101 difference binary. Now observe the following method borrowing across more than one column. Example: 100 binary minus 11 0. The borrow would be the minute in is 1001. Subtrahend is 1 to the base of 2. You'd have 111 to the base of 2 difference. Let's practice some subtraction, solve the following problems. All right, complementary subtraction. If you do any of the work with the computer, you will see and find out that most of the digital system cannot be subtracted. They can only be added. You go into the method of adding, give it the result of the subtraction of the sound. Think of it really is quite simple. The complement is used for our subtraction. The complement is something you complete something else. Is something used to complete something else. On most number of the systems, you will find 2 complement for the first amount with the necessary for the complete with the number for the highest number of the number system. And the decimal system move to being the difference between the given number for all of the 9s, and they'll call the 9 component complement with the radix of 1 or the radix of negative 1 complement. Example of 9 complements is 2. 9 complements of the 254 is 999 minus 254 would be 745. The second type of complement is the difference between the number of the next higher power with the most number of base. Example, the next higher power would be 10 above the 99 is 1,000. But the difference between the 1,000 and 254 is 746. It's called the 10 complement. The decimals number system. This is called the radix complement. The U of the complex. When you will use complements to subtract. Look at the magnitude of the product. The 3 important parts of the point that we should be mentioned before we start with the never complement the minute end, a minute end in a problem. 2. Always regard any of the carry beyond the number of the position of the largest original number. 3. Add the radix complement of the original subtrahend to the original minute end. This will have the same effect with the subtracting original number, looking at the base for the 10 equal, an example of which would subtract 38 from 59. All right, 59 minus 38 would give you 21, and the radius complement you'd have 100 minus 38 would be 62, and 59 added with the radius plus 62, complementing with the 38 would give you the disregarding any carry would be 121. Now let's look at the numbers for the most of the computers. Most computer Binary system, just decimal system that had nine radixes, -1, -10, and 10 radix complement. Binary system, type of the complement, but that's the 2 type of the 1 with the radix and -1 complement with the 2 radix complement. Binary system, the radix number -1 complement with the difference between the binary number and all of the L's 1. The radix complement is the difference between the binary number and the next higher power 2. But let's look at the quick, easy way with the radix -1 complement that you have with this change that you 1 each of the original number to 0. Each 0 original number to the 1 original number to 1 had been done with example. So you'd have 1 0 1 1 0 1 1 base 2 would be 100 100 radix 1 complementing. There are 2 methods of achieving the radix complement. But the first method, we perform the radix negative complement with the added 1, with the much easier, but the subtracting original number from the next higher with the power of 2. After the subtract, you have added to the borrow. Saying another way with each of the radix complement with the binary number, change the 1 to 0 and all zeros to 1, and then adding, for example, the term of the radix complement 1 0 1 0 1 1 0 base 2. Step 1 would be the radix complement 0 1 0 1 0 0 1 0 2. Adding -1 would be 1 base squared would be 1 0 1 0 1 1. The second method of obtaining the radius complement with a demonstrated with the binary number of 0 1 0 0 1 0 1 1 0 1 1 0 base 2. Step 2, the lowest least significant digit, working with the most significant digit, we're adding the digits there are up to adding the first one. So your first digit would be 0 1 0 1 1 1 0 or 100 base squared. Now the radius -1 complementing radians, first digit, radius x complementing the remaining digits. The radius complementing same number base method. And method 2. Now let's do the subtract with the radius complement that will give you through the subtraction of the 3 to the 10th from 9 to the 10th. That would be 0 0 1 1 base squared and 0 1 0 0 1 minuted. So 9 to the 10th, 9 with the base of 10, and 3 with the base of 10 equals 101 minuted minus 0 1 1 2. Subtract and leave the number minuted alone. 1 0 0 1 base number 2 remains 1 0 0 1 base number 2. Either the radius complement with the 1 1 0 1 radians complemented subtrahended. Step 3, the radius complemented found with step 2 with the minuted with the original problem. All right, so you'd have original minuted 1 0 0 1 base 2, radius complemented 1 1 0 1 base 2 subtracted, and difference with the original problem would be 1 0 1 1 0. Remember to discard any carrying beyond the side of the original number. The original problem had 4 digits with the discard. The carry expand with the difference of the 5 digits with the disregard with the significant to the computer indicate the difference of the power of the cover the where carry would read the difference directly without any further computation. Let's check the answer. All right, 1 0 0 1 equals 9 to the 10th. 0 1 0 0 1 1 2 equals negative minus 3 to the 10th, would give you 1 0. Disregard the 1. 1 1 0 2 or 6 to the 10th. If we do not have to carry the indicate the difference with the negative number, then indicate the difference with the radius complement that produce the correct answer. Let's look at the example that will explain the following. 10 to the base of 10, 5 plus from 5 to the base of 10, 1 0 1 1 0 0 1 base base 2 from 0 1 0 2 base of 2. You'd have 5 to the 10 base equals 0 1 0 1 2 minute in a negative 10 minus 9 to the 10 base 1 0 0 1 2 to the base of 2 would give you 4. You'd have negative 4 to the base of 10. Leave the minutes alone. 0 1 0 1 2 remains 0 1 0 1 2. Remain radius complemented subtracted equals 0, 1, 1, 1, radius complemented subtracted. As the radius is found, they would equal 11. The original minute ended is 101 base of 2. Two complements would be 0, 1, 1, 1. 2 would be 11, 0. Difference of the original problem. We do not have to carry this tells any of the computer the only difference of the answer of the negative. There will no carry the the radius complement of the difference in step 3 will then be have the arrive at the answer of the difference of the original problem. Let's do the radius complement step, and then the next check the number. Check our answers. All right, 0, 1, 0, 0, base number, the radius complement of the difference in step 3. Remember, we had not cared for the step 3 with the show of our own answer for the going negative to make sure they indicate the difference in negative. Let's check the answer for the problem. Shows 0, 1, 0, 1, base 2 equal to 5 to 5 to the 10th, 0, 1, 0, 0, 1 to the 2, minus 9, negative 10 to the 10th. 0, 1, 0, 0, 2 would be a negative 4 to the 10, base of 10. The try to solve a few tracks from the complemented method. All right. Moving on. The octal number system. The octal, the base of the number, the system, the commonly system, the computer, the become of the relation with the binary system, the useful programming, some of the type of the computers. Locally, look closely with the comparison binary octal system in table 1-3. You can see the one octal digit is equivalent value of the three binary digits. Therefore, the following example of the conversion of the octal 225 to the with the base of 8 to the binary is back and again further illustrated the comparison. All right, octals of binary 2 equals 0 1 0, 2 equals 0 1 0, 5 to the with the base of 8 equals 1 0 1 square to the base of 2. Binary to octals 0 1 0 2 0 1 0 2 1 0 1 0 1 0 2 5 to 8. Or your binary octal comparison to the 0th power of the 0, 2 to the first is 10, 2 to the second is 100, 2 to the third is 1,000. So that's your binary. Your octal 8 to the 0 is 0, 8 to the first is 10, 2 to the fourth is 10,000, and the unit number. The term that you've learned with the decimal of the binary section, and also you with the octal system units remain with a single object with the number that's still symbol that you represent one or more units. The base or radix. With the other system, the radix or the base of the number of the symbol, with the system, the octal system uses 8 symbols, 0 through 7. The base and the radix indicated by a subscript of 8. Position notation. Octal number system, positional number system, just the decimal system, you the power of the 10, of the binary system, you the power of 2, the octal system, you the power of the 8, to determine the value of the number of position. Following bar graphs show the position and power of the base. 8 to the third, 8 to the second, 8 to the first, 8 to the 0, radix, 8 to the negative 1, 8 to the negative second, 8 to the negative third. Remember the power exponents that indicate the number of the time of the base of the multiplied with itself, the value of the multiplication that is graphed at the base of the 10 is shown. 8 to the third equals 8 times 8 times 8, or 515 to the base with a base of 10. 8 to the second equals 8 times 8 equals 64 to the 10th. 8 to 1 equals 8 to 10, and 8 to 0 equals 1 to 10. 8 to negative 1, 1/8 of 125 to the 10th. 8 to the second 1 times 8, 1 over 8 times 8 equals 1/64, or 0.15625 10 to the 10th. 8 to the third 1 times 8 times 8, they're 512, or 1 over 512, or 0.19531 to the 10th. All numbers to the left of the radix exponent for the whole number to the right of the fractional number, the most significant digit and least significant digit, with the determine the most least insignificant digit octal number, the same as the rule of the u of the other numbers for the digit farthest to the left, and the radix of the most significant digit, and the one farthest radius of the radix point with the least significant digit. So the most significant digit, the radix point, and the least significant digit. And if the number with the whole number, the most significant digit with the farthest to the left of the radix point, with the least significant digit immediately with the left of the radix point, with virtually with the number of the fraction, only with the non-zero digit. Consider the radix point with the amount most significant and the least significant is a non-zero digit furthest to the right of the radix number. And adding addition of the octal number. The addition of the octal number to no difficult provided that you remember that any time the sum of the two digits exceeds 7 are carried or produced. A carry is produced. Compared to the two examples shown. 4 times 2, 4 to the 8 times plus 2, 4 with a base of 8 with a 2 to the base of 8 with an m equals 6 with a base, 6 octal. 4 octal plus 4 octal equals 10 octal. So we carried the 1, got like the octal addition to table 1-4 with the benefit that you with the custom the adding octal number to you with the table to simplify with the direction you with the example. Adding 6 to 6 with the base of 8 plus 5 to the base of 8 would be let's look at column 6 of the column X. In column X for the figure. The X locate the 5 and the Y. So you'd have 6 and 5 would be 13. The point Z, or the two columns intersect with the sum of the difference. You have 6 plus 5 at 8. The 13.8 spoken 1 through or spoken in 1 3 base 8 and 1 3 is 1 3 1 3 base 8. Sorry. If you use the concept of addition you have already learned, you already read the octal numbers will work through the solution of the following and problems. So you have 4, 5, 6 base 8 augmented with 1 plus 1, 2, 3 base 8 added in. You get 601 with 8 with the sum. 7, 7, 7, 1, 4 with a base of 8 augmented in plus 7, 6 as augmented equals 1, 0, 0, 0, 1, 12 the base 8 sum. As we mentioned earlier in this section, each time the sum of the column numbers exceeds 7, they carry is produced with more than the one carry is produced with 3 or more numbers of the be added. With example of 7, I'll get into with the 7 added in, 7 in the base added, 7 in base 8 added in. Some augmented the first 6, 8, and 6 to 8, and 6 with the base of 8 with a carry with the sum of the 6 with the base of 8. The second added to the 5 with the 8 base of 8 with a carry with the, we should write down 5 with the base of 8 with the 2 carry with the brings down with the sum of the shown. Alright, so you have 7 the base 8 augmented with the 7 the base of 8. We get you 6 base of 8 subsum plus 7 plus the second added the 25 base of 8 or 1 carry sub of the end problem. Now let's subtract some questions. Alright, subtraction of octal numbers. Subtraction of octal numbers follow the same with the subtraction from the number that either and any other number except for the one only variation in quantity with the borrow with the decimal system you have is to borrow with a group of the number borrow you have the only in a decimal system you have to borrow in a group of 10 to the base of 10. In borrow system you borrow a group from 10 to the base of 2. In octal system you will borrow 8 from the base of 10. Consider a subtraction 1 from the 10 by the decimal binary octal number system. Decimal 10 to the base of 10 minus 1 to the base of 10 is 9 to the base of 10. Binary 10 to the base of 2 minus 1 base of 2 is 1 base and 1 in the base of 2. Octal 10 to the base of 8, 1 minus 1 base of 8 would be 7 and 8 base of 8. And in each example, you cannot subtract 1 from 0, for you have the positive difference. You must use the borrow with the next column of the number. The less examine the above the problem. Show with the borrow with the decimal quantity with the clarity. Show the 10 to the base of 10 minus 1 to the base of 10, 9 base of 10, 1 and 0 with binary 2, 1 and 0 base of 2 minus 1 base of 2 is 1 base of 2. 10 to the base of 8 minus 1 base of 8 with 7 base of 8. Alright, so you're borrowing decimal borrow 10, binary borrow 2, octal borrow 8. When you have used the borrow column borrow the reduce by the number by the 1, the amount of the borrow as with the column minus did with the subtract with the following example show with the procedure. So you'd have 34 minute with a base of 2 minus the base of, so 34 with a base of 10 minute in minus 9 with the base of 10 is subtracted with the 25 difference. Alright, 46 with a minute in with a base of 8 with a minus 7 minus with the base of 8 with a 37.8 the difference with the base of 8. In the octal example, the 7 to the base of the 8 with it cannot be subtracted with the 6 to the 8 with the 8. You must borrow from the 4 with the reduce of the 4 by 1. Add 10 to the base of the 8 with the borrow with the 2 to the 6 of the base of 8. Minute of the subtraction 7 to the base of the 8 and from 16 base of 8. You get the difference of the 7 base of 8. When the number of the difference of the bring down with the 3 with the need with the number refer to the table 1-4 with the octal and the addition table you are familiar with the octal number that you with the table the subtraction file with the each direction located the subtract end with the column Y next file with the line with the intersect with the minute and the error Z. Remaining with the difference will be row with the X directly above this point. The do file with the following practices 765 with the base of 8 minus 448, and those were the questions. Check your answers adding by subtract end with the difference for each of the problem. All right, your hexadecimal number system, or hex number system. The hex number system is a more complex system in use with the computer. The name that derived from the fact that the system that uses 16 symbols. The beneficiary computer program because of the relationship with the binary system. Since 16 is in the decimal system is the fourth power of 2 or 2 to the fourth, one hex digit has a value equal to 4 binary digits. The table 1-5 show the relationship between the two systems. All right, so 0 to the second, 0 to 0, 2 to the 0th was 0, 2 to the first is 10, 2 to the second is 100 in binary, 2 to the third is 1,000 in binary, 2 to the fourth is 10,000 in binary, and then your hex system 0 is 16 to the 0th, and 10 is 16 to the first, and unit and number. Each of the is in each previous number. The the unit stand by the single object of the number. The hex system symbol that you the representative of the unit and quantity. The Arabic number that uses the Arabic numbers 0 through 9 are used along with the first 6 letters of the alphabet. You probably used a letter in math problems to represent the unknown quantities. But in a hex system, A, B, C, D, E, and F each have a the finite value as shown below. A to the 6th with the base of 16 is 10 to the 10th. B to the 16th is 11 to the 10th. C to the 16th is 12 to the 10th. D 16th is 13 to the 10th. E to the 16th is 14 to the 10th. F to the 16th is 5 to the 10th. The base radix. The base of the radix of the system is 16 with the representative number of the system. Using the system quantity expressed in the hex will be noted as subscript as shown in 16 as A3EF16. Positional notation. Like binary octal decimal system, the hex system of the positional number system powers are 16. Or you have the positional values as often the number of the following bars shown in the figure. Position 6 to the 13, 16 second, 16 the first, 16 the 0th. The hex the positional notation radix 61, 6 is the negative 1, 6 is the negative second, and 6 is the negative third. Multiplying base time by the number of the times indicated by the exponent will show the equivalent decimal value. 6 to the third is 16 times 16 times 16 is 4,960 to the 10th. 16 times 3 is 16 to the third. 6 to the third is 16 times 16 or 256 to the 10th. 6 to the first is 16 times 10, 6 to the 10, 16 times 0 is 1 is 10, the 16 to the negative first, 160, 0, 167, 21st, and then so on. All right, you can see the positional value with usually fewer system symbol position representative expressed with the number of the hex one in the decimal system. The following examples show the comparison. 625 to the 16th is equal to 1,573 to the 10th. The most significant digit and least significant digit. The most significant and least significant digit will determine the same manner of the other numbers for the following example. The most significant and least significant whole fraction and mixed hex numbers. The most significant digit would be 7 and 9, and then E would be 4 would be your least significant digit, and radix and base is 16. Your radix point, the most significant digit, and that would be the far to the left, the most significant and least significant digit far to the right. Your most significant digit far to the left, the radix point, and then your farther to the right with the radix point would be the least significant digit. Additional hex numbers. The additional hex number that may seem intimidating the first significant, but the next no difference for the addition with the other numbers if the same rule apply with certain combination of the symbols produced they carry with the other numbers, others do not. Some of the numerals combined with the produced as home represent with the bottom letter. After a little practice, you will be confident adding hex numbers as you're adding decimal numbers. Study the hex additional table of 1, 6, the the table to add 7 and 7. Look at the number in 7 below with the columns X and Y. The points Z will be the two columns intersecting and is the sum in this case 7 and 7 equals E. As long as the sum of the two numbers is 15 to the 10th, or less, only one symbol is used for the sum. So as long as the sum of the two numbers is 15 to the negative 10th or less, only one sum is used. Only one symbol is used for the sum. A carry will be produced when the sum of the two numbers is 16 to the base of 10 or greater. The following example. So 8 to the base of 16 plus 8 to the base of 16 is 10 to the base of 16. A to the 16th plus base of 10. A to the 16th is 17 to the 16th. Therefore, 17 sixteenths, the base of d 16th and plus 9 sixteenths is 16 sixteenths. And then it shows the x and y column, x and z columns, additional. Let's see. B is it goes. So remember that it goes 9. 0 through 9, then A would be 11, B, and then followed by A, B, C, D, and F. Okay, and 0, or otherwise, in between the 9 would 1 to the 8, 1 times A, 1 plus A would equal B. 1 plus B would equal C, 1 plus D would equal E, 1 plus E plus equals F, 1 plus F equals 10, and that makes a decimal system. All right. Okay, in the example, each column's straight addition can now carry. Here's the sum of 4 and A is E. Adding 8 to D is 15 sixteenths. Written down is write down 5 and carry the 1. Add the first carry to 7. The next column add some of the 8 to B. The result is 13 to the base of 16. Write down 3. Carry the 1. Since the only carry left to carry the left to add on, bring it down to complete this problem. Now, producing more complex additional numbers, you may find it easier to add the Arabic numbers to each column first. All right. Sum of 4 is E1 and 3 for the first column, 16 to 16 for the write down, 16 carry for the second for the 1, 1, 9, 7 equals 12. 12 to the 16 for the carry over the next column, add B and 2 for the sum of the D. Write down the sum of the line, now add the first column 1, 1, 5, then column C with the 13 the base of 16. Write down the carry, add 3, and then B with the sum of the is E. Write down E, bring down the final carry, complete with the problem. Now solve the additional problems. And, all right. Subtraction hex number. The subtraction hex number to look for the more difficult than the preceding sections you learned rules of subtraction. Now you need only to apply the rules of the new number. So the symbol may be different, the amount of the bar will be different, but the rules may remain the same. All right, so you have the x additional term of the following solution, following problem. A, B, C to the base of 16, the minute end with the 642, the base of 642 subdivided in. Working left to the right, first locate the subtract in the column Y with the first line with cross C, but until you reach C, the difference to locate with the column X directly above the C, but in this case A, even the same procedure. All right, so you have A minus 2 would be C minus 2 would be A, and B minus 4 would be 7, and A minus 6 would be 4, would give you 447 A decimal 16 base 16 difference. Now examine 7E 5E minute end minus 471 subtract end, which give you E minus 1 would be 4, 5 minus 7 would be when carry that would be it's like, all right, 4, and then show the difference of these different problems. In the previous example, when f was subtracted from 1 when f was subtracted from 1e, the borrower u, but since they cannot but subtract f from e, they have the positive difference. The borrower with the 10 the negative 16th was taken with the next higher value of the column. The borrower was added to the E, and the higher value column was reduced by 1. The following example shown below, more difficult problem. All right. it shows the 7 minus b 4a37 minute n minus 2c 4b and base 16, both with basic 16. 7 minus b would equal c. You carry a 2, and 2 minus 4, or this would all work down to c 16 difference. This is all new to me, so I'm trying to do it the best I can. In the first step, the b cannot be subtracted from 7. You cannot borrow with a 10. Borrow of 10 to the decimal 16. The next higher value with the column, add with the borrow with the 7th the minute end with the first of 17. The base of 16 minus 6b. The 16 equals c to the 16th. Reduce the number of which the borrow was taken 3 by 1. Subtract 4 by the base of 16 from 2 to the base of 16. All requires as shown below. Alright, for 4a37, your next bar would be 9, would give you E, and then you'd have 1de, 7 of the difference. Remember that borrow is 10 to the decimal 6, not 10 to the 16th, not 10 to the 10th. There may be times when you need to borrow with a column from 0 minute in to the end. In that case, you borrow the next highest value will provide the value of the geo column from the borrowing from. Alright, the subtract a from 7, you must borrow the from the first borrow from the 2. 0 becomes 10 to the 16th, 10 with the base of 16, which is given the borrow with the reducing 10 to the base of the 16, provide 1, borrow with from 7, the reducing 10 by base 16 from by 1, equals F, subtracting A, the base of 16 from 17, base of 16, give you D, the 16th, bringing down 1 and F, the difference of 1 FD, the 16th. Now let's practice what you've learned solving the following hex subtractional problems. Alright, conversion bases. When mentioned in the introduction chapter, digital computers operate with electrical pole of the pole for the absence or easily of the representative of the binary numbers of pole of the representative of the binary 1, lag of the pole of the representative of the binary 0, vice versa. The section of the chapter discusses the octal and hexadecimal number that both mentioned with their number of the system and the beneficial program that you will see with the layout of the section. Octal and hexadecimal numbers are easily converted with the binary into binary numbers or vice versa. If you're going to work with a computer, there will be many times where you will be necessary to convert decimal numbers to binary octal hex numbers. We will also be able to convert the binary octal hex number to the decimal number. The converting each number of the system, each for the others will be explained with the prepare. The converting from any with the base and other base will be needed. Your decimal conversion. Some of the computer systems are capable of converting decimal number to binary numbers. They do this by using additional circuitry. Many of these systems require the decimal number to be converted to another form before entry. Alright, decimals to binary. Conversion of decimal binaries either to any other base of the complement dividing the decimal number by the radius of the system that you by using you are converting to. The following definitions identify the basic terms used within division. Dividend, the number of the dividend, divisor, the number of the which the dividend is divided. The quotient, the number of the result of the division of the number of one number by another. The remainder, the final undivided part after the division is that is left at the lower degree than the divisor. The convert the base of the 10 a whole number to a binary equivalent. The first step of the problem is to have 2 times 5 to the base of 10 with divide the base of the 10 number to the radius 2 with the binary system extract with the remainder to become the binary at least significant digit. Alright, so 2 goes into 5, 4, and it makes 4 with a remainder of 1. The continue the division, dividing the quotient with the step of the radius of 2, squared 2. The quotient step of the 1, the 2, and then 2 is 2 divided by 2 is 1, 2 over 0 is 0, the remainder is 0. Quotient dividing quotient for the radius quotient becomes small for the divisor of the 1 division for the remainder for the most significant digit. 1 divided by 2 is 0. There's 0 over 1, remainder 1, the remainder is step of the least significant digit. Now rewrite the solution. You will see that 5 to the with the base of the 10 equals 101, 101, 2. Think of the following conversion of 23 the decimal of the base of the 10 to the binary set up the problem. 2 divided by 23 to the base of 10. By the number of extracts into 2 equals 1. 23 divided by 2 equals 11. And with the 2 open, that gives you a 3 minus 2. Remainder of 1, least significant digit. So you'd have 11 minus 2 divided by 2 would equal to 5, which gives you a remainder of 1. 5 divided by 5 divided by 2 equals 2. 4 over the 1, remainder of 1. 2 divided by 2 equals 1, remainder of 0. 1 divided by 2 equals 0. The quotient previous itself, the remainder of 0. 1 most significant digit. Rewrite the solution for the most significant digit from the most significant digit to the least significant digit. No matter how large the decimal number may be, even the same process, let's do the problem below. This is the larger dividend. 2 divided by 105 divided by 2, 52, with a 10 over 5, that will give you 4 and 1, least significant digit. Then you take 52 divided by 2 would give you 26, and 4 over 12 with a 12 with a 0 would give you 0 and if digit. 13 divided by 2 would give you, or 26 divided by 2 would give you 13, would give you 0 significant digit, and then 13 divided by 2 would give you 6 with a remainder of 1, and the 6 would be divided by 2 would give you 3, remainder of 0. 3 divided by 2 is equal to 1, and then 1 divided by 2 is 0 divided by 0 is equal to 1 most significant digit. Therefore, 105 the decimal the tenth equals 11010012. We can convert fraction decimal number to multiplying the fractional radix extraction portion with the product left with the radix point, with continued multiplying fractional portion with the previous product with the desired degree of accuracy attained. Let's go through the process of converting 25 to the base of 10 into the binary. So far that 25 to the base of 10 times 2 is equal to 0.50 is equal to 0 most significant digit. 0.5 times 2 equals 1 least significant digit. So the first figure to the left of the radix point with the most significant digit, the last figure with the computation, the least significant digit, rewrite the solution. Most significant digit to the least significant perceived of the radix point is shown. Now, alright, remember that the last one was in dividing in the last one, the most significant, and timesing the most significant digit is first. As we mentioned before, you should continue with the operation for the recheck of the desired accuracy. For example, the 0.425 the base of 10, the 5 places of the binary. 0.42 times 2 is 8.5. 0.85 is the significant digit of 2 times 2 is 1.70 of 2. Times 2 would be 1.4, and 1.4 times 2 would be 0. 2 times 1.6 would be 1. 2 times 1.6, 1.2 would be 1. And 2 times 1.2 times 0 is 0.4. 0 is a significant digit. Although multiplication was carried out with 7 places, you would only use what was described with the write out the solution, or 0.11012. Convert the mixed number of the 372625 binary, split the number, then solve the fraction component with this, solve each with the one, separate the problem, carrying with the fractional part with the 4 places with the conversion, each of those complete with the recombined with the radix point shown. 37 to the base of 10 is 1001012. 625 to the base of 10 is 101. 02 to the base of 2, 37.625, the base of 10 is 10010111012. Convert the following decimal number to the best binary. Alright, decimal to octal. The conversion of the decimal number to the base of the 8 equivalent is done with a repeated division, by repeated division method. You simply divide the base of 10 base 10 number by 8, extract the remainders. The first remainder will be the lowest significant digit. Last remainder will be the most significant. Look at the following example. The 15 decimal to octal with the setup of the principal 15 decimal by 8 divided by 8 is since the 8 goes into 15 would be 8 over the 7, which would be 7 would be the least significant digit. And then for You'd have 1 left over from 8 minus 7 would be 1 or most significant digit. Since they're based on 8, you'd have 1. So, like, now right at the number of the most significant digit, you'd have it shown as 1/7 of the decimal 8. Same process, regardless of the size of the decimal number. Naturally, more divisions are needed. Larger numbers. The following example: 264 decimal to octal. 264 decimal to octal divided by 8 is 33. 24 minus 26 is 240. 24. 24 minus 24 minus 24 is 0. Least significant digit. Then you take 33 divided by 8 would give you 4. 32, 1 significant digit. And then 4 divided by 8, 0. 0, 4, 4 would be the most significant digit. By rewriting the solution, we find that the octal equivalent is 264. The decimal 10 is 5. We'll convert the decimal fraction, multiply the fraction by 8. Each subtract everything that appeared to the left of the radix of the first number. Extract everything that appeared to the left of the radix of the first of the number that will be the most significant digit. Will follow the radix point with the least number to extract with the least significant digit. So you take 0.8 times 8 would be 0.4, or most significant 0 times 8 would be 3.2, the most significant digit. 8 times 1.6 is 0. And then 1, 4, and 6, least significant digit. Write the solution for the most significant digit, least significant digit. You can carry the conversion at many places as needed, but usually 4 or 5 places or another. Convert the mixed number to decimal octable system, split the number into whole fractional portions. Solve the solution below. All right, to convert 105.5 to 8 is equal. You're going to do this. You're going to do 105 first divided by 8 would be give you 35. The 25 minus 24 would give you the 1 significant digit. 13 in a decimal and an octal would be 8. So you'd have that goes into 8 one time. You get a remainder of 5 between 16. And then I don't know why I did 1. I guess there was a 1. Yeah, all right. 13 divided by 8 went 1. So 1 divided by 8 equals 0. 0. The most significant digit is 1. Least significant digit is, so you have which way would it write the solution from 1? Well, you'd have 151. Most significant digit 0.589. For the decimals, you times it by the 8, so you'd have 4.7.2 would be 4 times 8 to 569.5 times 8, 555.68 times 8, or 4. Your solution, your combined portion of the mixed number would be 151 radix 454 base of 8. Convert the following decimals to octal. Or decimal to hex. To convert decimal number to the base to the base 16, follow the repeat of the division. Proceed with the U of the convert binary octal. Only divide by 16. Looks at the example. So you have 63. In decimal to hex is 63 divided by 16 would give you 33 with a 48 with a 15 decimal. 15 would equal 5x 5/16, or lowest significant denominator would be at the top of the first digit. And you just take the 3 divided by 16 would give you 0, or 3 to the 16th, or most significant digit. So therefore your least hex equivalent is 63. The decimal 10 is 3 F16 to the base 3 F's to the basic 16, or hex. You have to remember the remainder is in base 10. You must be converted to a hex if exceeded by 9. If it exceeds 9. Let's work through another example. 174 of the base of 10 to the hex is 174 times the base of 16 would go 10, 16 minus 17, 17 minus 16 minus 17 would be 14, would give you 0. 14 decimal 10, but they give you e to the 16th, their lowest significant digit. You take the the 10 divided by 16, and you get 0, 0, a the 16th, and the most significant digit. So you'd have AE16 or AE16. The A to the AE, the basic 16, therefore probably various uses will vary. Have to convert the decimal fraction, hex fraction, occasionally arrive at the conversion due to another same manner binary octal. Use the following example of the pattern. Alright, convert 0.695 decimal to hex. So you take 0.695 times 16, they'll give you 11.20 with a base for the 16. Since they're like it goes 8 to 9, 1 through 9, and then 8 to 15, I think. So you'd have 11 times 11.120 times 16, 0.72, 1.2 times plus 1.200, 1.92, 1 to the base of 16. Then you have 5,520 plus 9.200 is 14.72. BE is the base of 16, and then you write this. Then you'd have 4.320 plus 17.2, 11.52. B the base of 16. So your answer would be B1EB, the base of 16. You should have need to convert the decimal mixed number to the hex to convert the whole number and the fraction separate with the recombine the solution. Convert the following decimal numbers to hex. Converting the binary octal hex number to the decimal equivalents is covered as a group later in this section. Alright, binary conversion. Earlier chapter we mentioned octal hex numbers are useful computer programs and much easier to provide with data with the computer and one other than city systems. Likewise, important to be able to convert the data from the computer into one another number the system that easily understand the data. Look at the following number: 10110110110111, or 27115 to the base of 8. You can easily use the actual number to most easier to say that although the two numbers look completely different, they are equal. Since 8 is equal to 2 to the third, then one octal digit represented the 3 binary digits as shown. Alright, so you have a 0 to the base of 8 equals 0 base base of 2. 1 to the base of 8 equals 0 to 1, 0, 0, 1, 2. 2 to the base of 8 would be 0, 1, 0, 2. 3 to the base of 8 with a base of 8 would be 0, 1, 1 base of 2. 4 with a base of 8 would equal 100 to the base of 2. 5 to the base of 8, 1, 0, 1 base of 2. 6 to the base of 8, 1, 1, 1 base of 2. 7 to the base of 8, 1, 1, 1 base of 2. We have the principle of the conversion binary. It's a simple example of the following conversion binary number to begin with this section. We write the binary number going to be converted, starting with the radix point and moving left. Break the binary number into the two groups as shown below. The grouping binary into groups of 3 is called the binary code octal. So you want to take your number from the left of the radix in steps of 3, and then add zeros to the left. Add zeros to the left of the most significant digit that will fill for a group of 3. Next, write down the octal equivalent of each group. 0, 1, 0 would be 2. 1, 1 would be 7. 0, 1, 1. 0, 0, 1 would be 1. 0, 0, 1 would be 1. 1, 0, 1 would be 2. 5 to the decimal 8 with a base of 8. To convert binary fractions, do the equivalent starting with a radix point from the right. Expand each digit into 3 groups. Add zeros to the right of the least significant digit if necessary to form a group of 3. Now write the octal digit for each group of 3 as shown below. Alright, so we'd have 100, 1004, 0011, 1106, 01138. Convert the mixed binary number starting with the radix point with the form of the group for the 3, both right for the form. So you'd have So we have 5, 6, 1, 6 to the 8th, and then alright, binary to hex. The table below shows the relationship between the binary and hex numbers. You can see that the 4 binary digits may represent 1 hex digit. This becomes 16 is equal to 2 to the 4th. 0 is equal to 000 binary, 1 is equal to 001, 2 is equal to 10, 3 is equal to 11, 0111, 4 is equal to 011, 100, 5 is equal to 101, 6 is equal to 110, 7 is 111, 8 is 1,000, and 9 is 1,101. A is 1010. B is 111, 111. 11. C is 1100. D is 1101. E is 1110. And 5 is 1111. Use relationship you can easily convert the binary number to the hex, starting with the radius point, but then move it to the right with the over the left break of the number, then into the group of the 4. With the group of the binary and 4-bit group is called binary code hexadecimal, or BCH. Alright, so converting binary number into hex is which is 16, so you'd have 4-digit numbers 1, D, and 3 after the radius, and then radius point. Add zeros to the left of the radius point, but the whole portion of the number to the right of the lowest significant digit form groups of 4. So, the 1112 to the hex, you'd have 1110. It'd be E the 16 to the hex, E to the hex, point E hex. In this case, 0 had not been added, but the conversion would have been 7 hex, which is incorrect, and convert the following binary into hex. Alright, octal conversion. The conversion of one number system to another was explained earlier, done with simplified computer programming, interpreting data, octal and binary from some computers, except for the octal data. Octal digits must be converted in binary. The process of reverse binary octal conversion. Given an octal number to binary, write octal number to the following number will convert 567 to the base of 8. 567 to the base of 8. Below each octal digit, write the corresponding 3 digits code for the octal equivalent. Solution 568 with equal 101, 110, and 111. Then remove the conversion from the format. 101, 110, 111 to binary 2. As you're given the necessary with the bilogical format. Old fraction was 0.123, 0.123. Hex is converted to the same manner as shown. 123 1.011 012 0112 binary. Alright, apply these principles regarded to makes as number 011 010 010 101 binary 2. Convert the following numbers binary. Alright, octal to hex. You will probably not run into many occasions of the conversion of the octal numbers to hex. Should you need the right of the conversion, 2-step procedure: convert the octal number to binary, then convert the binary to hex. The step to convert 553.78 to hex is shown. 101 3 1011 7118. And then you take your binary digits group from the 4 zeros, 2BE16, and convert the following numbers to hex. Hex conversion. All right, the procedure for the converting hex number to binary octal and are reversed for the binary octal conversion hex. To convert the hex number to binary, set up the number in the block format used earlier. The conversion block below each hex digit will write the 4-digit equivalent. Observe the following. For ABC, for the binary, you'd have ABC, and then hex. Just look at the conversion: octal, conversion, hex, octal. 2-step procedure: first convert the next binary, second convert the binary to the octal, and let's you the same as the example above the hex convert this. So you convert your hex to binary, and then your hex your binary to octal. Alright, conversion to decimal. Computer data will have the little meaning that they have meaning to you if you have not familiar with the various numbers of the system. Often necessary to convert these binary octal hex number to decimals. The need for the understanding is better they illustrate that showing you the paycheck for the printed in binary check in the amount of 10 million or 10,010,101 and .00 binary looks impressively, but relatively amounts to $149 .0 in decimal form. Alright, binary to decimal. The computer that calculates you prepare properly be the opposite of the binary number. The conversion take for the plate for the computer the amount with the print down into the check. Since the computer, however, does not automatically convert the binary to decimal, there are many times that you must convert them mathematically. Or to convert the base number 2 to the base 10, you must know the decimal equivalent of each of the power of 2. The decimal for the number of the power of 2 is obtained by multiplying 2 by itself of the numbers times by its exponent whole numbers. 2 to the 4th would equal 2 to the 16 would be equal 16 or 16 decimal. The fraction, the decimal value of the equivalent 1 by divided by 2 is in the item itself the number of the times indicated by the exponent. Looks at example. 2 to the negative third equals 1 times 2 times 1 over 2 times 2 times 2 times 2 or 1/25 decimal. All right, below the portion decimal value system, 2 to the 5th is 32, 2 to the 4th 16, 2 to the 3rd 8, 2 to the 2nd 4, 2 to the 1st 2, 2 to the 0 1. Radix 1, 2 to the negative 1st 0.5, 2 to the negative 2nd 0.25, 2 to the negative 3rd 1/25. Remember earlier in this chapter you've learned that any number of the 0 power is equal to 1 to the decimal. And the number method, any number method to determine decimal value with the position multiply the preceding value with the 2 whole number to divide with the preceding value with the 2 fractions as shown below. Alright, so you have a radix portion multiplied and divide by 2. From high side, whole number decimal exponents multiplied by 2, lower number to divide by 2. Let's convert binary number to the decimal using the positional notational method to write out the number that converted to the right in the decimal equivalent each position with 1 indicated as add these values to determine the decimal equivalent of the binary number. Look at the example. 1 would be 32, 0 would be 8, so we have 5 digits, 1, 2, 3, 4, 5, or a 6-digit number, 32, the middle number would be 8, then the last number would be 1, so you'd have 1 plus 8 plus 32, 41 to the decimal. You may write the decimal equivalent each position following example. Add only the values indicated 1, 1, 16, 8, 4, 0, 2, 1, 15, 25. So you'd add all the 25 to 4 and 16, 22 to the decimal 16. You should make the decimal value of each position properly aligned before adding the practice level of converting binary to decimal. Okay, octal decimal conversion, octal number to decimal, best for them with a positional notation method. The process is one with the converting binary enough to the decimal with determine the decimal equivalent of each position multiplying 8 by itself with the number that indicated with the exponent with the set of the bar graph of positional values is shown below. 8 to the 4th, 8 to the 3rd, 8 to the 2nd, 8 to the 1st, 8 to the 0th, 8 to 0, 8 to the negative 1, 8 to the 2nd, 8 to this. So you'd have 496 to the 512, 641, 81, 7 and 4, 8 to the 3rd decimal. Next multiply, shit, I don't know this one seems tricky. Alright, hexadecimal. It is difficult to comprehend magnitude of the base number 16 until they present with the base number 10. Until in base number 10. For representative E, 0, 16 is equal to 224. You must remember that usually the fewer digits necessary to represent the decimal in base number 16. When you convert base 16 to decimal, you may use the positional notation system of the power 16 in the bar graph. You can also convert the base number 16 in the binary, then convert it to the base number 10. You know the paragraph of each of the power of 16 result with a tremendous increase with the decimal equivalent, only negative power of 16 and negative first shown in the demonstrating purpose. So 16 to the 4th, 1, 2, 3, 4, 6, so that's 6 positions. Alright, so the number was 224, I believe. You must have the electrical conversion octal hex number, the digit for the appropriate decimal number, the position decimal base for this 18 with the value of the A through F of the decimal before multiplying. Let's take a look at the example. Convert 2C16 is equal to 16 times 2 and 1 times 16, 12 times 12 is 12. It give you 44 to the decimal 10. Our decimal equivalent to the 2C is equal to 44 to the decimal 10, or the base 10. You have the same procedure with the binary octal. Convert the base 16 fraction to the decimal. If you choose to convert the hex number of the binary, then decimal, the solution will be thus 2 times 0010, or 32, and the C16 1100 times 1100 times 2 is equal to 4. 4, 8, and 10. 4, 8, and 32 is 44. 10. Convert the base of the base 10, 16 to the base number 10. Alright, your binary code decimal. In today's technology, you hear the greater deal about microprocessors that integrated the circuit with the design of the two purpose data processing and control. Computer microprocessors both operate on circuit with electrical pulses called words. A word can be represented with a binary number such as 1011001112. Word length is described by the number as in bits, and the series of the 4 digits will call 4-bit word. A series of 4 digits would be called a 4-bit word, and so forth. Most common are 4, 8, and 16-bit words. Quite often, these words are the use of the binary code decimal points. Binary code decimal, binary code B or BCD method. The use of the binary digits to represent the decimal digit 0 through 9. Decimal digits represented with the 4 binary digits are shown. Your binary code decimal 001 is equal to 0001 is equal to 1, 001, or 10 is equal to 2, 11 is equal to 3, 4 is equal to 100, 5 is equal to 101, 6 is 110, 7 is 111, 8 is 1,000, and also 1,001 is 9. You should be able to talk about the best binary code decimal coding of the binary equivalent of the decimal digit. Since many devices with the binary code digit decimals known how to handle the system important, you must realize the binary code decimal of the binaries are not the same. With our example, the 49 of the decimal base 10 of the binary is 110. 1101, or you take 110. 11012, or binary decimal 42 binary code decimal would be 001, and then 001 or 1001. Each decimal digit converted binary equivalent. Alright, binary code decimal conversion. You can see how above the table the conversion of a decimal binary code decimal or binary code decimal to decimal is similar to the conversion of hexadecimal binary, vice versa. For example, to go through the conversion of 264 to the decimal binary conversion, use the block format that you give earlier. You first write the decimal in to be converted, then below each digit write the binary code decimal equivalent of that digit. You'd have 2, 6, and 4, or 10, 110, and 100. Binary code addition. The procedure for the following binary code addition is simple if you use the in binary. However, the possible addition of binary code digit values are invalid tools. Following examples: 1001 binary code is 9 to the 10th. 0110 binary code is 6 to the 10th. You give it a 15, 110. The sum of the 111 is equivalent to 15. However, the 111 is not a valid binary code number. You cannot exceed 1001 binary code digits, so the correction factor must be made. To do this, the 6 6 to the 10th or 0110 binary code to the sum of the two numbers that add the correction factors added the binary code decimal binary code digit greater than decimal group later than 1101. Remember, there's 1102, 1111, 1100, 1101, 1111, or 1100 decimal code. Remember, these are no binary code. The 1010 binary code, 1011 binary code, 1100 binary code, 1101, and 1110 and 1101. So invalid code. So you have 110. Shit. Some bolts adding conversion factor converted back to the decimal. Check the answer. Put answers develop and then add 6 process new bit for a word. All right, so 4 words, 4-letter words. All right, there's no 10. So okay. Remember that it's on a scale. So when you have 9 or 15, like this is getting complicated. All right, and now we have the summary. Remember the 4-bit words, and also so add shit. All right, we'll move on to the summary. The tape's getting long.